Welcome to this course on electromagnetic waves. Electromagnetic waves or electromagnetics is a subject which has fascinated human beings over many centuries. In ancient days, people used to ask questions like why the stars twinkle and the planets do not twinkle, or why there is a lightning, or if I put a magnetic needle in certain environments, why the magnetic needle deflects, how does the light reach from sun to the earth when there is no medium in between. And these kind of questions people try to investigate for many centuries. In the modern days, people have questions like how do we have a TV reception, how do we have a radio station operating, how does the mobile phone work, why the TV reception is good in some part of the house and it is not good in some other part, why we do not have a good radio reception inside a railway compartment, why the radio station which is at medium waves does not show any time fluctuation, whereas the radio station which is operating at short waves has time fluctuations, why certain things get heated when they are kept inside microwaves. And there are numerous phenomena which you see in the modern days which fascinate the common man. All these phenomena, either you take ancient phenomena or all these modern phenomena, the common thread which runs through all these phenomena is electromagnetism. In fact, in today's world, if we look around, there is hardly any gadget which does not work on the principles of electromagnetism. In this course of electromagnetic waves, we are going to essentially investigate the high frequency aspects of electromagnetism. Broadly, an electromagnetic phenomena can be divided into two categories, that is low frequency but high power and high frequency but low power. So, the phenomena like electrical machines, electrical power generation, transformers, distribution of electrical energy, they fall in the category of high power but low frequencies. Whereas, if you go to the modern systems like mobile communications, radars, satellites, optical fibers, they fall in the category of low power but high frequencies. So, in this course, essentially we are going to develop the principles of electromagnetics at high frequencies. We can ask very basic questions. If the frequencies increase, what way the electrical phenomena or the understanding which we have from low frequency circuits get modified? And then we can understand the various phenomena which I mentioned, which have a common thread, which is electromagnetic waves. So, electromagnetic wave essentially sees applications in many areas. Firstly, we have applications what are called transmission lines and high frequency circuits like radars or TVs or radios. Then we have application of electromagnetic waves in the area of what are called antennas, which can either transmit electromagnetic energy or can receive electromagnetic energy. We require knowledge of electromagnetic waves in a subject what is called satellite communication. We require knowledge of electromagnetic waves in the area of fiber optic communication. We require this knowledge in cellular or wireless communication. Electromagnetic waves find applications in radars and classical subject like radio astronomy, and also subjects related to electromagnetic interference and electromagnetic compatibility. So, in this course essentially we will try to investigate how time varying electric and magnetic fields behave, especially when the frequency of operation is large. So, as we all know that in general the phenomena of electromagnetism is governed by the 4 classical equations, what are called the Maxwell's equations. The Maxwell's equations represent the phenomena of electromagnetism in totality. However, as we proceed in this course, every time it is not required to go to the rigorous analysis of Maxwell's equations, and under certain approximations we can investigate the same phenomena in terms of voltages and currents, which are electrical circuits. However, as we go further, we find that representation of this in terms of voltages and currents become difficult, and then we can go to the general phenomena of electric and magnetic fields. So, let us first look at the electromagnetic spectrum. The word electromagnetic wave corresponds to any phenomena which is related to the time varying signals, time varying electric or magnetic fields. So, anything, no matter how small the frequency is, any frequency which is not 0 can be put in this category of time varying electromagnetic fields. So, what is shown here is the wavelength and then the physical dimensions which normally you see corresponding to those wavelengths. So, if you go to the very low frequencies, the radio frequencies, the wavelength is very large, and then the wavelength is comparable to size of a building. When you go to the microwave frequencies, the wavelength becomes few centimeter or about a centimeter, which is typically of the size of an insect. As you go further, the wavelength reduces and then the size becomes tip of the needle. When you go to the visible range of the electromagnetic spectrum, then essentially you are talking about size of the atoms or molecules, and when you go to X-rays and gamma rays, the wavelength becomes smaller or comparable to the atoms. So, the entire frequency range from very low frequencies to high frequencies can be summarized in one word, and that is the radio frequencies. So, in this course, when we refer to radio frequency, essentially we are referring to any phenomena which is not constant as a function of time, but it has a finite frequency. The same thing can be written in more technical terms, that here we have got the electromagnetic spectrum. These are the wavelengths starting from about 10 meters to 1 meter, then 10 centimeter, 1 centimeter, 1 millimeter, and all the way we go up to about 0.1 micrometers, which will be typically in the range of about X-rays, and these are the corresponding frequencies. So, 10 meter would correspond to 30 meters, 10 centimeter would correspond to 3 gigahertz, and like that when we go to this region where the wavelength is typically of the order of about 1 micrometer, the frequency will be typically of the order of about 300 terahertz. And then depending upon the frequency of operation, we use different media for transmission of the signals. So, in this region we use the media what is called the coaxial cables, whereas when you go to this range of wavelengths, we use the structure what are called the waveguides, and when you go to the very high frequencies in optical domain, then the media will be optical fibers. One can ask a very basic question at this point, and that is, why do we have to go to high frequencies? What advantage one gets by increasing the frequency? And one notices that if you consider a typical electrical system, the bandwidth of the system is more or less proportional to the frequency of operation. If we consider the major application of high frequencies as communication, then for transmitting more information, we require large bandwidth. So, as we can see from here, since the bandwidth is proportional to the frequency, by increasing the frequency of operation, one can get larger bandwidth, and therefore, one can transmit more information on a given channel. So, from information transfer point of view, increasing the frequency provides larger bandwidth and increasing the capacity of the information transmission. So, the first application which we have for electromagnetic waves, which is transmission lines, in which essentially we investigate how the voltages and currents are going to flow in a two conductor system, what is called a transmission line. So, a simplest system which we see all around, for connecting any electrical signal from one point to another, we require a pair of wires, and these pairs are twisted. So, this medium is what is called the twisted pair. You will see this kind of medium normally is used for telephone lines, and we want to investigate how the electrical signals will propagate on this structure. This media, the twisted pair, can handle low data rates, has a high electromagnetic interference, and is very lossy as the frequency increases. So, this medium normally is very useful for low frequencies, but as the frequency increases, the loss increases, and that is why this medium becomes not very attractive. As the frequency increases, then we go for a medium, what is called a coaxial cable, where we have a center conductor here, and then you have outer conducting shell. The high frequency signals are applied between the center conductor and the outer shell, and the signal flows inside this empty region here. This cable structure can handle data rates which could be typically of the order of about few megabits per second. This has low electromagnetic interference, and also it has moderate loss. So, to investigate propagation of energy on this structure, we require fundamentals of electromagnetic waves. As the frequency increases, even the center conductor of a coaxial cable adds to sufficient loss, and therefore, the surface area of the conductor is minimized, and in that process essentially we end up into a hollow pipe of metal inside which the electromagnetic waves can propagate. This structure is what is called a waveguide. So, if the cross section of this hollow pipe is rectangular, then we see that this waveguide is called the rectangular waveguide. On the other hand, if the cross section of this pipe is circular, then we call this waveguide as a circular waveguide. So, at high frequencies, typically at microwaves, the hollow pipes made of metal are used for guiding the electromagnetic energy. And again, you require a rigorous analysis of electromagnetic waves propagation inside these conducting pipes, and that helps you in finding out what will be the field distribution inside the structure, how the energy is going to propagate in this, how much energy loss will take place when it propagates inside this, and so on. The next application of electromagnetic waves is antennas. Now, antenna is a device which can transmit electromagnetic energy into the space, and also it can receive electromagnetic energy coming from the space. So, many modern equipments use the antennas, and here you see an antenna, what is called a parabolic dish. So, the radiation falls on this dish, gets reflected from here, and then there is here something called the feed. The electromagnetic waves get focused onto this point, and then it gets converted into electrical signal, and that electrical signal is processed further. The same dish, if the electrical signal is supplied to the feed, will generate electromagnetic wave, which will get reflected from this and will get into the space. So, antenna is a device which selectively puts the radiation in the desired direction. So, in fact, a simple antenna structure may not really provide the directional characteristics of radiation. Also, in modern days, we have got what are called the smart antenna systems, where the radiation characteristics of the antenna are automatically changed to maximize the reception of the signal. So, we require a thorough knowledge of electromagnetic wave propagation in the analysis of antennas or the smart antennas. Here is another smart antenna which has not one beam, but it has multiple beams, and beam can be switched or they can be placed inside the space on permanent basis, and depending upon which area the observer is, one can transmit the signal or can receive the signal from that zone. So, controlling the radiation characteristics is one of the important aspects of antennas. The next area where you require a thorough knowledge of electromagnetic waves is the satellite communication. The satellite is an object which is placed above the Earth's surface. So, here you see there is a satellite picture here, and this is the Earth, this is the satellite. So, this picture is taken from the satellite towards the Earth, and this is the station which is what is called the Earth station, which transmits the signal from the Earth to the satellite, and from the satellite to the Earth are received by the station. There are certain frequencies, bands assigned for satellite communication, what is called C band, S band, X band, K band and KU band. So, in this mode, essentially what we have an electronic system here with an antenna, and you are having what is called a Earth station here. The signal is transmitted from the Earth towards the satellite. The satellite receives this signal, converts its frequency, and then sends it down towards the Earth. And this signal which is coming towards the Earth can be received by the receiving stations on the Earth. So, one can establish a communication between any point on the Earth to any other point on the Earth. This whole propagation of electromagnetic radiation and proper placing of the radiation in a direction towards the Earth is controlled by the electromagnetic wave phenomena. So, essentially we require again a good understanding of the propagation of electromagnetic waves in investigating of propagation of energy from ground to satellite and from satellite to ground. Satellite is one of the modern communication transmission device. It has a relatively large bandwidth. It can transmit the data which can be self monitored, and it provides you a mobile environment. So, in fact, before the optical fibers came, satellite was one of the modes of transmission and with a large bandwidth. Later, as the time progressed, the fiber optic communication came, and then the knowledge of electromagnetic waves is required for investigating the propagation of light inside the optical fiber. So, here you see a set of optical fibers. Here is a very thin structure which is made of glass through which the light is propagated, and we require a good theoretical understanding of propagation of light inside this, because as the light propagates inside optical fiber, the signal gets distorted, and unless we understand fully how the signal gets distorted, one will not be able to tell how efficiently or properly the data can be transferred on this medium, which is optical fiber. Similarly, the devices which are used for optical communication, which are lasers, again require a good knowledge of electromagnetic waves. Then when you come to the wireless communication, which is the most modern mode of communication, then again you require various aspects of electromagnetic waves. So, here you see the father of radio communication. This is the hertz. He is doing some measurement on radiation. This is the environment where you see there are a lot of gadgets which all works on electromagnetic waves principle. Here is a mobile phone. So, all this together you see today in a mobile environment, all these devices are working on principles of electromagnetic waves. In this modern communication, what is called a cellular communication, we have what are called the base stations, from where the signals are transmitted, and then you are having users which are located inside what is called a cell. So, any mobile call which we make goes from the handset towards base station, and then the call is diverted to the appropriate user. So, we have a constant communication between a mobile handset and our base station. So, again you require a good propagation model in this environment, and especially when we are talking about this environment in cities where we are having large buildings and structures which are having a lot of reflection and refractions of electromagnetic waves, we essentially have a very complex electromagnetic environment. So, as the object moves inside the structure from the base station towards the receiver, one not only gets the signal which is coming directly from the base station to the user, but you also get the signal which are coming after reflections from these objects. So, what one receives at this location is a combination of the signal which is coming by the direct path, as well as the signal which are reflected from the buildings and other objects which are in the vicinity. Now, as the object moves, the total signal which you receive here is essentially an interference of all those signals which leave from multiple paths. So, as this vehicle moves, the lengths over which the signals travel, they change, and as a result you get a phenomena of interference which could be either constructive or destructive. Whenever we have a constructive phenomena, you can have a strong signal, whereas if you have the destructive phenomena, then one gets very low signal, because there is a cancellation of the signal. So, one notes then that as the vehicle moves, the signal varies as a function of time, and that phenomena essentially is called the fading phenomena. And to understand this fading phenomena properly, one requires a good modeling of propagation of this electromagnetic waves in this complex refracting environment. To avoid this phenomena what is called fading. One can create systems where the reflected and refracted signals are not received by these objects. So, if you make the receiving antennas not what are called omnidirectional, but suppose they are directional, and if they can receive signal only coming from this direction, then the reflected signals contribution can be reduced, and as a result the effect of fading can be reduced. So, again you require good design of the antenna systems, which again require a good knowledge of electromagnetic waves, so that the multipath interference in a mobile communication can be reduced. We can again use the adaptive antenna system essentially to reduce the interference, and especially if you are having the environment which is mobile, then one has to keep changing the direction of reception as the vehicle moves. So, you require some kind of a smart antenna or adaptive antenna. The another application of electromagnetic waves is radar and remote sensing. So, as we know, radar is a device which is used for finding the distance of an object. So, the principle of radar is as follows. We are having an antenna here which is excited with an electromagnetic pulse. This pulse is radiated by this antenna into the space. The pulse goes and hits the object, and part of the energy is reflected from the object, which again is picked up by this antenna and is processed in the detector. Then, by knowing the time delay of this pulse, one can estimate the distance of the object, and also if the object is moving in the radial direction, then one can measure the change in frequency of the signal, what is called the Doppler shift, and from there one can estimate the velocity of the object. So, the radar essentially uses the electromagnetic pulse to find the distance and the velocity of an object. Again, since we are transmitting a very high frequency electromagnetic energy here, we require very special designs for these antennas, and also we require certain techniques by which the resolution of this device can be improved. So, there could be either signal processing techniques, or there could be even electromagnetics techniques which can be used to enhance the resolution of the radar. In general, essentially we have the antenna what is called a monostatic radar. So, the signal goes from the radar antenna to the object, get reflected from here and gets received from here, and the received power one can calculate. So, you require a good modeling firstly of the propagating medium, and also a good modeling of the scatterer or the object from which this energy is going to be reflected. So, in fact, a parameter what is called the effective cross section of an object requires a very good modeling of electromagnetic waves. In fact, there is significant work has been done in modeling different objects and finding the radar cross sections of objects which are made from different materials and which are of different shapes and sizes. The radar is also used for remote sensing, and that is, if you have a vehicle here which can send the radar pulses down towards the earth, and the reflected energy is measured by the radar. As the vehicle moves, essentially we can get the reflectivity of the terrain at different locations. Then, by combining this information which is coming from different locations on the earth, essentially one can create a map of reflectivity of the earth's surface. And since the reflectivity depends upon various parameters like what is the vegetation, what is the conductivity of the earth's surface, whether it is a water body, one can essentially do some kind of a mapping from this reflectivity measurement to the actual objects on the earth's surface. So, remote sensing is one of the very important field where modeling or knowledge of electromagnetic waves plays an important role. To improve the resolution of radar in remote sensing, one uses a technique what is called a synthetic aperture radar. For an antenna like a parabolic dish, the angular resolution is approximately given by the wavelength of operation divided by the size or the diameter of the antenna. So, one can see that to get a very fine resolution in an image which we have got from remote sensing, we require a very large aperture. These kind of large apertures cannot be very easily created, especially on the vehicles which are moving like aeroplanes or satellites. So, a very clever technique what is called the synthetic aperture radar technique has been developed, where the antenna size is small, but the vehicle moves, and as the vehicle moves the reflection information is stored, and after all the reflection information are collected from different locations, then a data processing can be done to get an angular resolution which will correspond to the total distance travelled by this vehicle. And this technique is an extremely powerful technique, because without having a physical aperture or physical antenna, one can effectively realize an aperture size which could be of the order of tens of kilometers, and therefore one can improve the angular resolution substantially. So, again you require good analysis of electromagnetic waves, and if you go to the synthetic aperture radars, then you get very nice characteristics. That firstly you get a very high linear resolution from this radar, which is independent of the range, though it requires very large data processing. So, electromagnetic waves find very active application in investigation of synthetic aperture radars. The same technique is used very actively in a branch of physics what is called radio astronomy, where the signals which are coming from the sky are measured. So, a typical radio telescope would look something like this. The signals are coming from sky. What you have is a very passive receiver, nothing is transmitted in this case like radar. So, we have an antenna, the signals are received, they are frequency converted, detected and processed, and again we would like to know precisely from which direction a radiation is coming, or in other words, by a radio telescope one would like to get an image of a sky with as large a resolution as possible. So, again this limit what is called the resolution limit lambda by d comes into picture, and to get a very fine resolution of the image of the sky one requires very large telescopes. Again, since realization of very large telescope is very difficult, one again falls back on the technique what is called the aperture synthesis technique, as we saw in case of radar. But in this case we have now set of antennas which are located on the earth. Each antenna might look like that or could be some other shape, and then by collecting the information from all these antennas one can actually have an effective dish which is of this size. So one sees that each dish here, which is a primary antenna, which could be of the order of about tens of meters, but by using this technique, one can create an aperture which is typically of the order of about tens of kilometers, and therefore one can get an angular resolution which is far better than what one can get from a single dish. So radio astronomy is one of the areas where again the knowledge of electromagnetic waves plays a very important role. It helps you in designing very effective antennas and thereby giving a very high quality maps of the radio sky. This is the same picture of an array which synthesizes an aperture which is of this size. So this dish is of the diameter 25 meters, but the total spread of the antenna is of the order of 21 kilometer, and therefore we get an effective aperture which has a radius of 21 kilometer, though each antenna has a diameter of only 25 meters. This is the image which you get from the sky, and you can see very high angular resolution you can get. This is another object which you can get in the sky. So these are the areas in which essentially you see very active applications of electromagnetic waves. So though the phenomena is very basic phenomena, and as I said, this phenomena has been under investigation for many centuries, the focus or the emphasis is changed depending upon the applications. So in today's scenario, when we are having the communication dominance, we see a variety of phenomena which are related to high frequencies and which have direct application in the areas of communication. So this course essentially deals with the subjects which are the high frequency phenomena, and when you are having so many signals which are at high frequencies present in the environment, then it is natural to have the interference created by one system to the other. So then we require techniques to mitigate the electromagnetic interference, and that's what essentially is done in this branch, what is called EMI DMC. So EMI is the electromagnetic interference. So first we investigate, study how a high frequency device would create interfering signals, and then what are the ways by which this interference can be reduced. In fact, any time varying signal, and if it is varying at a very high frequency, then it will create a lot of interference. Take a simple device like inside a computer, a switch mode power supplies where the current is switched at a very high rate, it creates a lot of electromagnetic interference. So if you are having any other instrument in the vicinity, one sees interference created because of this high switching current. One would also remember we may get interference on our radios whenever somebody starts a car or a scooter in the vicinity, because whenever we start a scooter there is a sparking, and because of that spark you get electromagnetic interference which is picked up by the radio, and then you get disturbance on your radio. So as you are having more and more devices which are operating at high frequencies, the environment now is having lot more interfering devices, and therefore it is essential to investigate the techniques by which the interference can be reduced, or one has to find mechanism by which the devices can be isolated, what is called shielding. So one can shield the devices from one another, or the devices become more and more electromagnetic compatible. So, today whenever we design a electromagnetic gadget or electrical device, it is mandatory to make it electromagnetic compliant, so that it does not create additional electromagnetic interference which will affect the other systems. So, in this subject essentially we are going to discuss the high frequency aspects of electromagnetics, which is electromagnetic waves. So, we have topics. First we talk about the transmission lines, where we still deal with voltage and current. Up till now we have developed our understanding of the circuit in terms of voltages and current. Suddenly if we start talking about electric and magnetic fields, it might appear that we are talking about totally different subject. So, in transmission line essentially we make a slow departure from our low frequency circuit analysis to the high frequencies. So, what we try to do, we still retain the terminology of the circuit, that is, we talk about voltages, currents, circuit parameters like inductance, capacitance, resistance, but we introduce the concept of space, and then naturally we show that as soon as the concept of space is introduced in the circuit analysis, we get the solutions for voltages and currents which are waves. So, we get a phenomena of electromagnetic wave, though in the form of voltage and current, but that gives at least the foundation of a wave phenomena, though this is going to be related to voltages and current. So, we are talking about only scalar quantities, but that provides at least some feel for the electromagnetic waves. Once that concept is understood, then we go to the next topic in this core, which is Maxwell's equations, which are the foundation of the electromagnetics. So, we starting from the basic laws of physics, establish the mathematical equations, what are called the Maxwell's equations. Then we ask what is the solution of the Maxwell's equations in a medium, how the electric and magnetic fields exist inside a medium, and then we start with a very simple case, that is a medium which is unbound, and then we find that the solution which we get for Maxwell's equations in that medium is a uniform plane waves. Then we go further and then try to investigate how this uniform plane waves would behave when there is a medium discontinuity. So, how the energy transfer takes place from one medium to another medium if there is a sudden change in the medium properties. This comes under this topic of reflection and refraction from media interface. Then we make the medium which is a spatial medium, that is a conducting medium. So, then we take the reflection of the electromagnetic waves from the conductors, and naturally we migrate into a structure what is called a parallel plane waveguide. The parallel plane waveguide is a structure which is essentially two conducting sheets parallel to each other, and the electromagnetic energy propagates between these two sheets. And later on we modify this device to what is called rectangular waveguide, where we put two more parallel planes perpendicular to the earlier planes, so that you create a pipe in which the electromagnetic energy is trapped. So, if you see from here to here, the journey of this course is essentially to capture the electromagnetic waves into more and more bound region. So, we start with the unbound medium in this case, then we go to this one where we try to just put a boundary so that the wave is confined in half of the space. Then we try to capture the waves between two boundaries. Finally, we try to capture the wave inside a pipe, which is called a rectangular waveguide. Then later on in this course, we discuss the basics of radiation that is under what condition the radiation will take place, and the very basic device or the very basic element which can give radiation is what is called the Hertz dipole, is investigated. And then by using this knowledge, one can go to the more practical antennas, what are called the linear antennas. Following which then we go to more complex systems, what are called the antenna arrays, and that will give us the knowledge of how to manipulate the directional characteristics of radiation from the antennas. So, these are the topics which will be covered essentially in this course. Now, before we close this, let us look at some of the devices which work on the principles of electromagnetic waves. The simplest one is this coaxial cable which you have got. You can see here, this is basically a transmission line. You can see there is an outer conductor here and there is a center conductor. So, electromagnetic energy propagates inside this, and as I mentioned earlier, these kind of structures, transmission lines, are used at frequencies up to few gigahertz. Then the devices which are based on electromagnetic waves is this structure, what is called an horn antenna. So, you see this is in the shape of a horn. There is a connector here which is of coaxial type. So, electromagnetic energy is connected at this point. This excites this structure which is the waveguiding structure, and then by flaring this waveguide in this shape, essentially the radiation goes into the space. So, this device is an antenna which is normally used at microwave frequencies. Then we are having guiding structures, optical fibers, and this is the optical fiber which is made of plastic. One can see here there is a inner portion here through which the light is guided, and the light can now go through the structure, can emerge very efficiently from the other end of the fiber. So, by using optical fibers, the electromagnetic wave in the form of light can be sent over very, very long distances. This is another optical fiber which we have here. This is very thin, typically of the order of about 125 micron. So, the thickness is little thicker than hair. And this is the fiber actually is used in practice for sending the information over very long distances. So, you see all these devices which we are seeing here, either a coaxial cable or a horn antenna or an optical fiber, all of this require a thorough knowledge of electromagnetic waves. So, basically this course on electromagnetic waves is the foundation course for time varying electric and magnetic fields, and predominantly its application is towards communication, but there are many other applications also which are not communication related. For example, microwave ovens, in which the things can be heated by using microwaves, work on the principles of electromagnetic waves. So, in this course we are going to build the concepts of high frequency circuits and the basic phenomena of time varying electric and magnetic fields, which are electromagnetic waves.